Hello, and welcome to this quiet corner of the night, where you can learn the strangest and most beautiful facts about the galaxies scattered across our universe, even as you fall asleep. I'm so glad you found your way here tonight. Maybe the day behind you was a long one. Maybe your thoughts are still carrying small things they picked up somewhere along the way. Or maybe you're simply the kind of person who would rather drift off among distant galaxies than lie there counting sheep. Whoever you are tonight, you've arrived in the right place, and there is nothing left for you to do now but rest. So let yourself settle. Let your breath slow and lengthen without your help. Let your shoulders loosen and your body grow heavy and weightless at the same time, as if gravity had quietly eased its hold, just a little, just for you. Nothing ahead of this will ask anything of you. My voice will stay low and unhurried from here to the end, and the music will stay soft beneath it. No rise, no sudden turn, nothing that lifts you back to the surface. It can keep you company all the way through the night, if you'd like it to. Tonight, we're drifting far from home, out past the tidy spirals in the textbooks, to the galaxies that never learned to behave. Some of them wear rings of young blue stars around a golden heart. Some trail long ribbons of starlight behind them, drawn out by a neighbor that passed too close. Some are so faint and so widely spread that they are barely there at all. And some shine from a single, small point at their center, brighter than all the stars around them combined. There's no hurry. We have all night. If these gentle journeys are becoming part of your evenings, a like or a quiet word below helps another sleepy soul find their way here too. And now, let's drift out slowly among the strangest galaxies in the sky. Let's begin with something calm and surprising. A few galaxies shine most brightly not because of their stars, but because of the black hole at their center. That sounds turned around, since a black hole is known for keeping light rather than giving it away. But the brightness never comes from the darkness itself. It comes from the material drifting inward, gas and dust gathered into a disk that grows so hot it pours light out across the whole spectrum. In some galaxies, that one small glow outshines the billions of suns around it. What you are seeing, in the end, is gravity slowly becoming light. The picture most of us carry of a galaxy is a neat one, a graceful spiral or a smooth, glowing oval drifting in silence. Then, astronomy hands you the odd ones. Some look as though their arms have been drawn loose. Some carry a bright ring around an almost empty middle. Some lean to one side, bent or creased, as if they remember being touched. These shapes are not decoration. A twisted disc can point to an old encounter. A ring can mark a passage straight through the center. Each unusual outline stops being a shape and becomes a story. A galaxy can go on making new stars long after it should have grown quiet. Astronomers once imagined a clean division, Young galaxies, blue and busy. Older ones, red and quietly done with all of it. Real galaxies turned out to be less obedient. Some that look settled and aging still find a way to spark fresh rounds of star formation. New gas may drift in from outside. A small companion may be taken in and deliver its material. Cooling clouds may collapse again into nurseries. So the path from youth to rest is not one way. A galaxy can pause and quietly begin again. Some galaxies are meeting each other right now in the slowest possible motion. The word collision suggests something sudden, but these encounters unfold with enormous patience. Two great systems begin to pull at one another long before they ever merge. Their shapes stretch, their gas clouds stir. Their stars are drawn out into long, curving trails. All of it continues for ages beyond any human measure. The antennae galaxies are the best-known example, caught halfway through their long meeting, with streams of stars reaching far out into the dark. When we look at them, we are seeing a conversation still underway. Once you look past the textbook spirals, the variety becomes almost playful. And astronomers have named these galaxies after the most ordinary things: wheels and spindles, hats and cigars, soft bubbles of light hanging in the quiet. The nicknames are more useful than they sound. They remind us that a galaxy is a real structure with a real orientation, and that changing our angle can turn one familiar kind into something else entirely. Add a passing neighbor, a season of new stars, or a lane of dust, and the appearance changes again. Shapes solid enough to turn over in the hand. Some galaxies keep a companion at the end of one arm. The whirlpool is the loveliest example, a wide, open spiral seen almost perfectly face-on, its arms traced in the blue of one newborn star's. And there, at the tip of one arm, sits a smaller galaxy, apparently resting against it. The two have been passing each other for a long time, and that slow, gravitational tug is part of why the whirlpool's arms are drawn so clearly. It looks like a hand holding something small. In truth, it is two galaxies in the middle of a very long, very gentle meeting. Here is something quiet and strange. In a familiar galaxy, you'd expect the stars and the gas to move together, all sharing one broad direction. Some galaxies simply don't. Astronomers have found systems where the gas turns one way, while a population of stars at the center turns the other. That is a strong clue the galaxy did not grow alone. It likely drew in material from outside, and rather than blending, the newcomer kept its original motion. In an ordinary image, the galaxy looks perfectly calm. Only when we measure how its light moves does the hidden choreography appear. A galaxy can hide most of itself in something we cannot see. When astronomers measure how quickly stars and gas move through many galaxies, the visible material never seems to supply enough gravity to hold everything in place. The outer regions travel too fast. By ordinary reckoning, they should drift apart, and yet they stay. The leading explanation is dark matter, a form of mass that gives off no light at all and shows itself only through its pull. In some galaxies, it outweighs everything luminous many times over. The beautiful structure we admire may be a small, bright thread inside something far larger. Gravity is usually introduced as a tidy rule. Heavy things attract other heavy things. In real galaxies, that simple sentence creates astonishing complexity. A close pass can draw out trails of stars, hundreds of thousands of light years long. A merger can fold elegant spiral arms into something rounder and smoother. Gas is pressed into new star-forming regions, while other material drifts outward or sinks toward the center. None of it is random. It is the sum of countless objects answering each other's pull at once. In these galaxies, you can almost read gravity directly from the shape, working patiently at an enormous scale. It's easy to think of unusual galaxies as distant curiosities that belong somewhere else. Our own Milky Way is a gentle correction. From the outside, it looks fairly orderly, and yet its past was anything but quiet. Long streams of stars arc through its halo, and many are thought to be the remains of smaller galaxies, drawn in and spread out over billions of years. One of the largest of those arrivals, now called Gaia Enceladus, seems to have joined us more than 8 billion years ago, and its stars still travel differently from the ones born here. The thick disk around us may hold traces of encounters older than the sun. This story is not only far away, it is also the story of home. Few galaxies look as deliberate as Hoag's object. At its center sits a round, warm yellow gathering of older stars. Far around it floats a nearly perfect ring of young blue ones, and between the two lies a wide, empty gap. The whole thing resembles a golden eye opened in the sky, so symmetrical that people often mistake the photograph for an illustration. It is real, and astronomers still discuss how it came to be. An ancient encounter, perhaps, or a slow reshaping from within. The universe does not only make disorder. Sometimes it makes something improbably composed. The Cartwheel Galaxy earned its name honestly. The bright outer ring really does look like the rim of a wheel, with faint spokes reaching toward the hub. Astronomers think it formed when a smaller galaxy passed straight through the disk of a larger one, sending a ripple traveling outward through gas and stars. That ripple gathered material as it went, and new stars lit along its path in one sweeping circle. It is like watching a splash spread across a still pond, except the pond is a galaxy, and the ripple is measured in light years, moving slowly enough that we see it held in place. Some galaxies wear a glowing ring of newborn stars around a much quieter middle. At first, the pattern feels decorative, as though the galaxy had lit itself for display. The truth is more physical. A bright ring usually marks a region where gas has been pressed together firmly enough to collapse into new stars, while the center has been cleared or has simply finished its busiest season. In many spirals, a straight bar of stars guides gas inward and gathers it at a certain distance, and a ring of soft new light appears there. Star formation is not always a general glow. Sometimes it chooses one lane. Polar ring galaxies look like one galaxy wearing another as a ring. There is a main body, often broad and smooth, and then a second ring of stars, gas and dust, orbiting almost at right angles around it. The likely explanation is a long, patient borrowing, material drawn from a passing companion that settled into an unusual orbit and stayed there, stable enough to last. Each polar ring is a visible record of something acquired. And because the ring circles the galaxy in a plane all its own, it lets astronomers weigh the invisible dark matter around the system in a way an ordinary galaxy never could. From Earth, the Sombrero Galaxy looks dignified and a little unlikely. A bright central bulge swells upward like the crown of a hat, while a narrow lane of dust runs across the middle, marking the flat disk seen almost edge-on. The nickname is irresistible, though the structure behind it is better still. That central region is unusually large and thick with older stars, giving the galaxy a deep glow at its heart, and the thin, dusty disk around it blocks just enough light to sharpen every line. It sits somewhere between the familiar categories, refusing to belong entirely to either. A spiral galaxy, seen face-on, shows you broad arms and open curves. Turn that same galaxy sideways, and the view changes completely. The disk compresses into a slender line of light, so narrow it can look like a scratch across the darkness. This is why a few are called needle galaxies. Their thinness is partly a matter of orientation, but it is also a reminder of how genuinely flat these disks are compared with their width. Seen from the edge, dust lanes cut through the glow like dark seams, and the central bulge rises gently above the line, revealing the whole architecture in silhouette. The Black Eye Galaxy carries a broad band of dust across one side of its bright center, and the effect is unmistakable. A soft, dark curve laid over the light. Dust lanes like that are made of fine grains mixed through gas, and they can block starlight so completely that a piece of a galaxy seems to be missing. Here, the uneven arrangement points to an eventful past. Astronomers believe this galaxy took in a smaller companion long ago because the gas in its outer regions turns one way while the inner regions turn the other. A memory still slowly rotating. Messier 82 looks narrow and compressed from where we sit, but the real story is what is happening inside. This galaxy is in the middle of a starburst, forming new stars far faster than usual. Such activity does not stay quiet. Massive young stars shine fiercely, live briefly, and end as supernovae, pouring energy into the gas around them. In images, red plumes reach out above and below the disk, as though the galaxy were breathing outward. The likely cause was a slow encounter with its larger neighbor, Messier 81, which stirred its gas and set all of this in motion. Centaurus A tells its history right on the surface. The main body looks like a large, smooth galaxy, and yet a thick lane of dust crosses it in a way that feels entirely out of place. That lane is rich in gas and dust, and almost certainly came from a smaller spiral galaxy taken in long ago. Rather than blending away, the borrowed material stayed and still gives the galaxy its distinctive band. There is more to it. The black hole at its center is feeding, and radio telescopes reveal enormous jets reaching far beyond the visible stars. Two stories at once. The tadpole galaxy trails a long ribbon of starlight behind it, stretching so far that the whole system seems to be swimming slowly through space. That tail was not left by motion through empty darkness. It was drawn out by gravity during a close passage with another galaxy, which lifted stars and gas away from the disk and stretched them into a single luminous stream. And within the stream, bright clusters of new blue stars have formed. A tail like that looks at first like something lost. Look a moment longer, and you find new light beginning inside it. Many galaxies never had spiral arms at all. The sweeping pinwheel is famous for good reason, but it is far from universal. Some galaxies appear smooth, or gently boxy, or simply undefined, with their stars spread in ways that feel less ornamental and more plainly physical. That absence matters, because spiral arms are tied to motion and to the way gas and stars organize themselves across a disk. Without them, a galaxy tells a different story about how it formed. Once you accept that the universe owes us no symmetry, the sky becomes a good deal richer. Irregular galaxies ignore every neat category. They may have no central bulge, no defined disk, no obvious balance, only scattered bright regions and uneven clumps that feel unfinished. Often, the cause is company. Gravity from a nearby galaxy can pull and press a smaller one until its ordered structure gives way to something rougher. The small Magellanic Cloud, drifting out near our own Milky Way, is the best known example, pulled and stretched above all by its long relationship with the large cloud beside it, as the two of them fall toward us for what may well be the first time. Their asymmetry is not a failure of design. It is evidence that gravity is still at work. Dwarf galaxies are small, and still they reshape their larger neighbors. These systems hold far fewer stars than the great spirals, yet they often serve as the raw material from which bigger galaxies grow. When a dwarf drifts toward a larger system, gravity unspools it and spreads its stars into long streams. Those streams do not simply vanish. They add mass, alter motion, and leave traces astronomers can still find billions of years later. Repeated over cosmic time, such arrivals help build halos and thicken disks. Importance in the universe, it turns out, is not always a matter of size. When a small companion begins to fall toward a giant galaxy, the process is anything but quick. Gravity loosens its material gradually, drawing stars and gas away across many long orbits. So the gathering happens in stages, a slow transfer rather than a single moment. The Sagittarius dwarf offers a vivid example close to home. It is being unwound even now. Its stars wrapped in streams that loop around our galaxy. These are not leftovers. They are the visible architecture of growth. A galaxy can be gathering a neighbor for billions of years, and what it gathers slowly becomes part of the shape it keeps. Not every galaxy announces itself. Some are spread so thinly that their stars scatter across a wide region with very little gathered light. And against the blackness of space, they look like faint smudges that are barely there. They are real galaxies, all the same, with stars and mass and long histories, only diluted over such an enormous area that they are easy to miss entirely. There is something appealing in that. These systems quietly challenge the idea that a galaxy has to be obvious to matter. Some galaxies never command the sky at all. They are simply present in it, waiting to be noticed. Ultra-diffuse galaxies can be as wide as the Milky Way and hold only a small fraction of its stars. Imagine taking a substantial galaxy and thinning it until its light is spread across a volume so large the whole thing turns faint and fragile. Some of them live inside crowded galaxy clusters, where gravity is rough and delicate systems might be expected to come apart, and yet they persist. Astronomers are still working out how. Some may have lost their gas early. Others may sit inside unusually heavy halos of dark matter. They feel like galaxies stretched almost to transparency. There may be galaxies that hold gas and mass and almost no stars at all. It is an idea that quietly questions the way we notice galaxies at all. Usually, we find one because its stars shine. A dark galaxy would be different. A system rich in gas, wrapped in dark matter, with too little star formation to make itself known in visible light. Astronomers search for candidates by listening for clouds of hydrogen, or by watching the motion of visible neighbors. The universe may build some of its structures long before it lights any of them. Starlight is not the only thing that makes a galaxy visible. In certain systems, the glowing gas is the most striking feature of all. Gas shines when it is warmed, when intense radiation strips electrons from it, or when it is stirred by star formation, or by activity near a central black hole. Under those conditions, hydrogen and other elements emit in distinctive colors that telescopes capture beautifully, revealing filaments and loops and broad, soft patches hanging around the galaxy like weather. The glow becomes a map of energy at work, the visible breath of processes that would otherwise stay hidden. A galaxy can be real and heavy, and still very nearly invisible. Whether we see something depends on how its light is gathered, what kind of light it makes, and whether our instruments happen to be tuned to catch it. A galaxy with few stars, or widely scattered stars, or stars behind thick dust, can be overlooked even when it holds a great deal of mass. And most of that mass may not shine at all, if dark matter carries the larger share. So there can be a deep difference between what looks important and what actually holds a system together. Low surface brightness. Galaxies hide in plain sight. They are not necessarily small and not necessarily far away. Their light is simply spread so thinly across the sky that they blend into the background, and a large galaxy can sit unnoticed in an image for years while brighter neighbors draw the eye. They are not concealed behind anything exotic. They are concealed by understatement. Many turn out to be rich in gas and dark matter with only modest star formation, evolving slowly and gently. The sky still keeps secrets, not because they are impossibly distant, but because they shine so softly. Ring galaxies may form when one galaxy passes straight through another. It is a fine example of a rough event leaving something elegant behind. As the smaller galaxy crosses the disk of the larger, it sends a wave of compression racing outward, rather like a ripple spreading across water after a stone touches the surface. Only here, the surface is a galaxy full of gas and stars. Where the wave passes, gas gathers, and new stars begin to shine, tracing a widening circle. Long after the visitor has gone, that circle remains, a single crossing still written in light. Two colliding galaxies almost never bring one star against another. That feels unlikely until you picture the scale properly. Galaxies look crowded in photographs, but the distances between their stars are enormous. And even when two systems pass entirely through each other, the chance of one star striking another is vanishingly small. What actually meets is the larger structure. Gravity reshapes both. Gas clouds run together, gather, and begin making stars. Orbits shift, tails and bridges appear. So a galactic collision is not a pileup of suns. It is two vast swarms drifting through one another, rearranged by their shared pull. A merger is not one event. It is a sequence of meetings, partings, returns, and a final settling. Two galaxies may first brush past each other and continue on, only to be drawn back together over immense spans of time. With each pass, they lose a little energy, stir each other's structure, and come nearer to union. Stars are redistributed, gas sinks inward, and the two invisible halos of dark matter overlap and combine. Seen across the universe, mergers form a gallery of every stage at once. Each curve and plume records something unfolding with extraordinary patience. A close passage between galaxies can draw matter outward with astonishing reach. Instead of remaining in tidy disks, stars and gas are pulled into long, elongated streams called tidal tails, glowing faintly across distances that are hard to hold in the mind. Sometimes one galaxy grows a tail. Sometimes both do, and the pair seems to be gently unraveling in opposite directions. These streams carry information about the masses involved, the angle of approach, the closeness of the pass, and here and there along them, new star clusters form from material carried out into the open. Bridges are what happens to the matter caught in between. During a close encounter, gravity can draw stars, and gas into the space that separates two galaxies, so they appear linked by a single luminous thread. A bridge turns an invisible force into something you could almost put your hand against. You look at it and feel the pull. Gas within the bridge sometimes collects into knots of new stars, so the space between the galaxies becomes an active place rather than an empty one, a temporary architecture built while gravity decides where matter belongs. A merger can fold a spiral galaxy into a smooth ellipse. Spirals are known for ordered disks and elegant arms, and those arrangements are more delicate than they look. If two substantial galaxies combine, the repeated gravitational stirring can undo the rotating disk that once kept the stars in a single flattened plane. Their orbits scatter into many directions, and over long ages, the result becomes rounder, thicker, more three-dimensional. It is a slow folding of one shape into another, taking longer to finish than the Earth has existed. And the galaxy it leaves behind often looks like the calmest thing in the sky. Gas can rest inside a galaxy for a very long time without making many stars. Then a passing neighbor changes everything. As galaxies draw near, gravity presses their gas clouds together, slows their drifting, and guides material into denser regions. Once enough gas gathers, it collapses, and star formation rises sharply. A modest-looking system can begin to shine with young, hot stars. So an encounter that pulls a galaxy out of shape can also start the most productive season of its life. In some galaxies, the clearest evidence of an old meeting is not a mark. It is a bloom. Astronomers often speak of two galaxies dancing, and the word is well chosen. When a pair becomes bound by gravity, they do not always merge at once. They may circle one another, draw close, separate, and return, with every passage changing the shape of the next. Seen over enough time, it resembles a long, slow choreography. Tidal arms lengthen, cores brighten, gas drifts inward. From a distance, the pair can look almost tender, two luminous forms leaning together. And the ending is already written. Once enough energy has been given up, they will become one galaxy. Some of the strangest galaxies are simply snapshots taken partway through a change. The universe offers us the same process at every stage at once, so we can assemble a long story from scattered moments. A galaxy midway through a meeting might show a twisted disk, a double center, a stretched tail, or a bridge reaching toward a companion. Each of those tells us we are not looking at a final form. These galaxies are not so much separate kinds of object as dramatic chapters in an ordinary life. A galaxy can spend hundreds of millions of years looking nothing like itself, suspended between one identity and the next. Large galaxies often grow by taking in smaller ones. A dwarf companion drifts inward, begins to lose its stars and gas to the tides, and is gradually unwound until its material belongs to the halo or the disk of the greater galaxy. This is not a rare accident. It appears to be one of the ordinary ways galaxies assemble themselves across cosmic history again and again, which means a galaxy can become grand, not by remaining untouched, but by gathering others into itself. Streams, shells, and unusual motions all linger afterward, so that every large galaxy is partly a collection of older ones. Most galaxies make stars at a pace that is impressive by our standards and modest by cosmic ones. A starburst galaxy is different. For a limited season, it can produce new stars many times faster than usual, as though some long-held reservoir of gas had finally been let loose. It often follows an encounter or a merger that drives material into dense regions where collapse becomes unavoidable. Massive young stars appear in great numbers and bathe everything around them in light. A starburst is not a way of life. It is a phase, brilliant, generous, and by its nature, brief. A galaxy's gas is the raw material of every star it will ever make, so spending it quickly carries a cost. In certain systems, star formation becomes so efficient that the supply is consumed far faster than usual. Instead of a slow, steady pace across long ages, the galaxy enters a short and dazzling season of overuse. For a while it shines with new stars and glowing regions, and the brightness contains its own ending. Because once the gas is turned into stars or carried away, the pace falls off. There is something moving in a galaxy spending its future on a luminous present. Young stars are brilliant, and in many starburst galaxies, their light never escapes cleanly. Thick dust absorbs much of it and warms in the process, then releases that same energy again at infrared wavelengths. So a galaxy that looks modest to the eye can be pouring out light in the infrared. This changed astronomy in a deep way, revealing a whole population of intensely active galaxies that had been easy to underestimate. Dust turned out not to be a nuisance, obscuring the view. It became the signal, the place to look for where everything is happening. In many unusual galaxies, the most energetic regions are wrapped in so much dust that visible light alone gives a misleadingly quiet picture. Dense clouds absorb and scatter the light of newborn stars and of active central regions, keeping their true brilliance inside. But that same dust warms and glows at longer wavelengths, so the story reappears in infrared and radio light. It is a quietly satisfying reversal. The material that conceals the action is also the material that announces it. First appearances in astronomy are rarely the final word. A newborn cluster of stars can be crowded with brilliant young suns and still be difficult to see if enough dust lies in front of it. The fine grains mixed through the gas absorb blue light especially well and redden whatever gets through, sometimes hiding a region almost completely. In galaxies forming stars at a great rate, those dusty regions can be vast. Infrared light passes through far more easily and reveals what was there all along. A galaxy may hold billions of young stars, while an ordinary image shows only fragments of them. Abundance kept behind a very fine veil. Before infrared astronomy came into its own, some galaxies seemed unremarkable, dusty, subdued, moderately busy. Then astronomers looked at longer wavelengths and found something extraordinary underneath. Beneath the muted appearance, several of these systems were releasing enormous amounts of energy. Their hidden starbursts and buried nuclei warming the dust until they became among the most luminous objects known. It was a lesson about the narrowness of our own eyes. A galaxy can wear a calm face while immense processes continue behind it, and the sky rewards those who learn to look in other kinds of light. In a galaxy making stars quickly, the youngest and heaviest stars live briefly and end brightly. Their radiation, their stellar winds, and their supernovae pour energy into the surrounding gas, and when enough of it gathers in one region, the gas is driven outward in a great flow known as a superwind. These winds rise above and below the disk in vast, soft plumes, carrying warm gas and heavier elements out into the space between galaxies. It is a curious kind of exhale. The same process that fills a galaxy with new light also begins to send material gently away. When a galaxy drives a strong enough flow, some of that gas may never return. In smaller galaxies especially, the pull of gravity can be gentle enough that the outflow carries material away for good. That matters because gas lost to space is gas that will never become another generation of stars. The galaxy is not merely rearranging its clouds. It may be quietly reducing what it can build later. There is a kind of symmetry in it, a season of creation so bright that it begins to empty the very system it lit, one long, slow breath at a time. There is a paradox resting at the heart of every starburst. The more efficiently a galaxy turns gas into stars, the sooner it may end the conditions that allowed the burst at all. Gas is consumed or warmed until it resists collapsing or carried outward by winds. Over time, the pace of creation quietly undermines the material for more creation. Astronomers see galaxies that grew still after their most active seasons, left with older stars and very little cold gas. The brightest chapter can also be the opening of a much longer, quieter one. Extremes are difficult to sustain. Many of the most interesting galaxies are caught somewhere in the middle. They are neither calm star factories with long futures ahead, nor systems fully at rest in old age. Gas is still present, but under pressure. New stars are forming, and so are the winds that may slow the next generation. A merger may be delivering fresh material, even as feedback begins to warm it. This in-between condition is part of why these galaxies feel so alive. Building and depletion are visible at once. Such a galaxy has not become what it will be, and it cannot remain what it was. At the heart of most large galaxies rests a supermassive black hole, and only some of them become bright. The difference is food. When enough gas and dust fall inward, they do not simply drop through and disappear. They gather into a tight, fast disk, press against one another, warm, and release an astonishing amount of energy on the way in. That light can outshine the entire galaxy around it. The black hole itself stays perfectly dark. It is the material on its way inward that becomes a beacon, gravity doing its work with remarkable efficiency. Picture a whole galaxy full of stars, and then one small region at its center, growing so luminous that it takes the entire scene. That is what happens when matter is funneled toward a supermassive black hole in quantity. The gas forms an accretion disk, and friction within that disk raises temperatures high enough to radiate across the spectrum. Ultraviolet, visible light, X-rays, and more, streaming out from a region you could very nearly fit inside our own solar system. Billions of suns may be spread across the galaxy, and still, the brightest point of all is that one small circle of falling matter. When quasars were first found, they seemed almost impossible. They looked like points of light, nearly star-like, and yet their light showed them to be enormously distant. If they were that far away and still so bright, their power had to be beyond anything expected. The answer was that these were not stars at all, but galaxies whose central engines were extraordinarily active, supermassive black holes being fed on a grand scale, pouring out radiation from a small region, while the surrounding stars faded into the background. The brightest things in the universe are not always the biggest. Some quasars can be seen across most of the observable universe. Their light began traveling when the cosmos was young, and it is still bright enough for our telescopes to gather. So we are not only seeing extreme brilliance, we are seeing ancient activity preserved in light that has been traveling for most of cosmic history. Astronomers use them as beacons from deep time, reading the material their light passed through on the way. To look at a quasar is to receive a signal sent from an age long before the Earth, by a heart bright enough to survive the journey. If you're still here with me, let this be a soft reminder. Nothing ahead will change. My voice stays low, the music stays where it is, and there are no rises left in the hours to come. You are free to stop listening whenever your body decides. The rest of this will keep drifting along beside you, either way. Some galaxies send narrow jets of particles and radiation out from the region around their central black hole. When one of those jets happens to be aimed almost directly toward us, the galaxy appears exceptionally bright and changeable, and we call it a blazer. The machinery is not unusual. What changes is our angle. Because the beam points our way, its light is boosted, and the galaxy seems far more dramatic than it would from any other viewpoint. It is a lovely reminder that strangeness in astronomy is sometimes a matter of where you happen to be standing. In visible light, a radio galaxy may look like any other large galaxy with a bright center. Then, radio telescopes reveal something far greater. Enormous jets extend outward from the core, carrying energy well beyond the body of the galaxy. And at their ends, great soft lobes form where the jets meet the surrounding gas, structures that dwarf all the visible starlight. the familiar galaxy turns out to be only the middle of a much larger system, shaped by power we cannot see with our eyes. The stars we noticed first were merely the beginning. A jet from a black hole can reach farther than the galaxy that made it. This sounds like an exaggeration until you see the images. Launched from the region around a supermassive black hole, these narrow beams can stay focused across extraordinary distances, crossing beyond the visible body of their galaxy, and continuing on until the galaxy itself seems small beside them. The physics behind them is still being studied. Magnetic fields, rotation, the conditions close to the black hole. Even so, the picture alone is enough. A tiny center throwing long, disciplined lines of light out into space. An active galactic core is not always steady. Its brightness rises and falls over time, and sometimes surprisingly quickly, which is itself a clue that the source is very small. If a whole galaxy were brightening together, the changes would be smoothed out across enormous scales. But a compact central region can vary as the flow of matter shifts, or as ripples move through the disk feeding it. That makes these cores feel less like lamps and more like weather. Inside an ancient system of stars, something is keeping a rhythm measured in days and months and years. Not all of a galaxy's activity happens where our eyes would notice. Some look modest in visible light, a calm body of stars with a dusty middle. And then, at radio wavelengths, they become extraordinary, with jets and lobes and structures the optical image barely hinted at. It is one of the great lessons of modern astronomy. The universe does not owe its most important truths to the narrow band of light we happen to see. A galaxy can whisper one story in starlight and tell quite another in radio waves, and both of them are true. The brightest hearts in the universe are not powered by fire. When we think of great brilliance, we usually think of burning, because stars shine by fusion in their cores. The most luminous galactic centers need no such thing. Their light comes from matter falling inward. As gas descends toward a supermassive black hole, it gives up gravitational energy, and that energy can be converted into radiation with remarkable efficiency. In some conditions, more efficiently than fusion. They are not fires. They are gravity engines. The same force that holds a galaxy together can, at its center, make it shine. A Seyfert galaxy is pleasantly deceptive. At first glance, it may look like an ordinary spiral, its stars arranged in familiar order, with no sign of anything unusual. Then the core gives it away. Bright emission and unmistakable spectral lines showing that the central region is far more active than the rest of the galaxy suggests. These sit somewhere between the everyday and the extreme, showing the same basic phenomenon as a quasar in a form that feels closer to hand. The house looks entirely ordinary. Something restless and powerful is going on in one small room. A supermassive black hole can be feeding and still stay hidden from view. Around some galactic centers, dense, dusty material gathers into a thick, shrouding structure that blocks much of the visible light depending on the angle from which we happen to look. Two galaxies with nearly identical engines can therefore appear entirely different, simply because one offers us a clearer line of sight. This idea sits at the heart of how astronomers unify the active galaxies, and it is deeply satisfying because it turns a mystery into geometry. The nucleus is not absent, it is only turned away. Visible light is easily stopped by dust, and X-rays are not. That makes them a fine tool for finding activity in galaxies whose centers look unremarkable. A system may appear to be a calm disk or a smooth body of old stars. And then X-ray observations reveal a compact, energetic source right at the middle, and the story changes. What seemed quiet becomes a galaxy with a feeding black hole at its heart. There is something almost detective-like about it. Each wavelength lifts a different layer, and the higher energies reach closest to the center of all. A galaxy can look entirely peaceful while its center is busy. The outer regions may hold calm old stars, graceful spiral structure, or a smooth, diffuse glow that suggests deep stability. Meanwhile, at the very middle, gas and dust are being drawn steadily inward toward a supermassive black hole. The process is rarely dramatic, in the sense of everything vanishing at once. It is selective, patient, and often out of sight. So, a serene appearance is no guarantee of a quiet core, and in some galaxies, the most consequential thing happening occupies a region tiny beside the whole. The influence of an active center does not stop near the black hole. Jets and outflows push energy into the surrounding gas, warming it and keeping it stirred, which makes it harder for that gas to cool and gather into new stars. This idea sits close to the middle of how galaxies are thought to evolve, because it gives the center a say in the future of the whole. A galaxy may hold plenty of gas and still form very few stars, if the gas is never allowed to settle. The center does not only shine, it also helps decide how much of the gas around it will ever grow still enough to become anything. In some galaxies, astronomers can see gas moving inward and outward at the same time. The light from the center carries both signatures at once: material drifting down toward the black hole, and material lifting away again in a slow wind. New stars may be gathering in one arm, while another arm grows quiet. From far away, such a galaxy looks like a single, settled object traveling in one clear direction. Closer in, it is a long negotiation between holding on and letting go, still unresolved after billions of years, and in no particular hurry to decide. For something so small, a central black hole has a remarkable say in what its galaxy becomes. Its mass keeps step with the properties of the bulge of stars around it, which hints at a long shared history. More than that, the energy released when it feeds can affect gas across scales vastly larger than itself, driving winds, launching jets, warming material enough to slow the making of new stars. If it grows quiet, gas may cool again, and other processes take over. A region small beyond imagining helps decide whether an enormous system keeps growing or settles. Not every active center shines steadily. There is evidence that some pass through cycles, with seasons of feeding and radiance followed by long, quiet intervals. A galaxy may glow brilliantly while material reaches its black hole, then dim as the supply falls away, and perhaps wake again much later when something new drifts inward. Astronomers infer these rhythms from structures that outlast the brightest phase, glowing gas still lit by a source that has since faded. It means a galactic heart is not a fixed thing. We are always seeing one brief chapter of a much longer story. A black hole does not have to announce itself to matter. If it feeds behind dust or radiates mostly in light we cannot see, or wakes only occasionally, it can still shape the galaxy around it, stirring gas, guiding motion near the center, quietly influencing how many stars form later. This is why astronomers work so carefully to find the hidden ones. Missing a nucleus means misreading the whole galaxy. A story that seemed to be about mergers or dust or ordinary aging may need rewriting once the concealed center is recognized, and the larger life around it suddenly makes sense. The centers of active galaxies often look wrapped in shadow. Dust lanes and obscuring material make those regions appear dense and closed, and the contrast with the surrounding light only deepens the impression. Yet that is exactly where the most powerful processes are underway. Matter is spiraling inward. Temperatures are climbing. Magnetic fields are shaping jets. The darkness there is not emptiness. It is the doorway of an engine. Astronomers learn to read it differently, not as absence, but as a sign that the light is hidden, redirected, or leaving in a form our eyes were never made to catch. Lenticular galaxies sit somewhere between the spirals and the ellipticals, and seem quite comfortable there. They have the flat disk of a spiral, without the sweeping arms that make a spiral easy to recognize. And at the same time, they can look as smooth and settled as an elliptical. Some may be former spirals that used up or lost the gas needed to keep their arms lit. Others were shaped by crowded surroundings that gently stripped their material away. What remains still remembers the disk it once was, without the full flourish of spiral life. Some galaxies lost their spiral arms and kept their disks. It is a gentle kind of transformation, and it shows that a familiar pattern can fade without the whole structure coming apart. A spiral arm is not a solid object. It is a pattern tied to motion and to the gas and young stars that light it up. If that gas is stripped away, warmed, or simply used up, the bright young stars that traced the arms disappear over time. The disk remains, broad and flat as ever, softened into something smoother. A galaxy quietly haunted by a former self. An elliptical galaxy can seem almost serene at first. Its light spreads in a rounded glow, with no obvious arms, no dust lanes, no bright clumps. Inside, though, the stars are not moving in one ordered plane, the way they would in a disk. They travel on many crossing orbits, making a far more intricate internal arrangement than the surface suggests. Hot gas may fill the whole system and shine in X-rays, and a supermassive black hole may still be shaping its future. The smoothness itself is often the result of long mixing rather than of stillness. The largest elliptical galaxies did not arrive at their grand, smooth form by growing quietly alone. The evidence points to a long history of joinings. Smaller galaxies combined, and then larger ones combined again, until the result became immense and rounded and rich in old stars. Each event stirred the orbits within and softened whatever structure came before. Over billions of years, repeated mergers built the giants that now sit at the centers of galaxy clusters. A giant elliptical is like a city built from the stones of older cities, remade so thoroughly that the original streets have disappeared. Some elliptical galaxies hold surprisingly little cold gas. That absence matters, because cold, dense gas is the raw material of new stars, and without much of it, a galaxy's future grows quiet. Many ellipticals are dominated by older reddish stars for exactly this reason. Where the gas went is one question, and why it never returned in usable form is another. Past activity may have warmed it. Surroundings may have carried it off. The central black hole may have kept it stirred. The result is a galaxy that shines beautifully while making very little that is new. Not every elliptical is perfectly smooth once you look closely. Some reveal faint arcs, nested shells, and ripple-like features in their outer light. And these faint arcs are among the finest clues a galaxy can leave behind. They can form when a smaller galaxy drifts in, and its stars spread along particular orbits, slowing and gathering at certain distances, which leaves delicate shell patterns, like waves held in place around the host. The effect is subtle, which only makes it more appealing. What first seemed featureless begins to show texture, and the texture turns out to be memory. Those faint arcs are extraordinarily dim, and for a long time, nobody saw them at all. They emerge only in long, patient exposures, where a telescope gathers light hour after hour until structures far fainter than the glow of the night sky begin to appear. And their spacing carries a number. The farther out a shell sits, the longer ago its stars were set on those long orbits, so the arcs can be read a little like rings in wood. A meeting that ended before the sun existed, still legible for anyone willing to wait for the light. Appearance can be gently misleading. A galaxy may present a rounded, polished, thoroughly settled face, and that calm exterior can be the product of old disruption rather than of peaceful growth. Mergers and repeated close passages can rearrange earlier structures so completely that the final result looks simple. Dust disperses, young blue stars fade, tidal features weaken until only a smooth glow remains. But the consequences stay inside. Stars on mixed orbits, streams in the halo, a black hole grown during old episodes of feeding. Smoothness is not always innocence. Sometimes it is what time makes of motion. An encounter between galaxies may end, and the shapes it made can linger for an extraordinarily long time. Tidal tails, warped disks, shells, off-center rings, and unusual streams of stars do not fade the moment the meeting is over. They remain as long-lived signatures, letting astronomers reconstruct events that are already deep in the past. The universe is patient with its clues. It leaves asymmetry and drifting debris in place long enough for someone to come along and read them. A galaxy can still look unusual, even when the reason has been gone for billions of years. Here is a thought worth turning over slowly. A galaxy that seems placid and rounded and thoroughly settled may owe that very appearance to ancient encounters. Repeated mergers can undo disks, mix stellar orbits, and smooth away every obvious trace of what happened. So what remains looks quiet, not because nothing happened, but because it finished long ago, and the pieces blended into one calm whole. Their stillness is the last chapter of a very long story. In astronomy, serenity is sometimes what enormous forces leave behind when they are done. Some galaxies turn around a center that is rotating the other way. Astronomers have found systems in which the innermost region spins in one direction, while the outer parts spin in another. And this is among the clearest signs that a galaxy's history involved something arriving from outside. Material gathered from a companion can settle in a way that preserves its own original motion, leaving a core that no longer matches the rest. In an ordinary photograph, the galaxy may look entirely usual. The strangeness is hidden in the movement, waiting for someone to measure it. In some galaxies, one population of stars circles one way, while another circles the opposite way. That is a remarkable arrangement, because it means the galaxy did not make all its stars from one well-behaved rotating disk. Material must have been added later, carrying its own direction with it. Gas drawn from a passing neighbor, settling into reverse motion, and then forming stars of its own. The result is a galaxy holding two histories at once, written into stars that pass one another, going opposite ways. Motion becomes the record of everything the galaxy has gathered. A few galaxies contain two disks turning against each other. A disk galaxy usually suggests one broad, rotating system with everything sharing a common direction. And yet, here are two distinct disk-like components moving in opposition. One likely formed first, while the other was built later from gas that arrived turned the other way and settled before making its stars. The arrangement is stable enough to last a very long time, and strange enough to reveal an unusual past. It is hard to imagine a clearer sign that a galaxy is assembled, rather than simply born. All of this hidden motion is found in the same gentle way. Astronomers spread a galaxy's light out into its colors, and because movement toward us tightens the waves a little, and movement away stretches them, every part of a galaxy quietly reports its own speed. Modern instruments do this across the whole face at once. building a map in which one side leans faintly toward us and the other leans away. A photograph gives you a shape. This gives you a shape that is turning, and now and then turning in more than one direction at once. A galactic disk looks perfectly flat from far away. In truth, a great many are gently bent, twisted, or lifted along their outer edges. These warps show that a galaxy's outer structure stays responsive long after any major encounter appears to be over. An old merger, the pull of a companion, or an uneven halo of dark matter can all keep a disk from settling into a perfect plane. What makes warps so lovely is that they are not dramatic distortions. They are lingering tugs made visible, evidence that a galaxy is pliable and still adjusting to something long past. Some galactic disks bend the way an old vinyl record does when it has been left too near the warmth. It is a homely comparison for something enormous. One side of the disk lifts slightly, the other dips, and the whole shape acquires a soft curve. The cause is gravitational rather than anything to do with heat, an old interaction, or the way new material settles into the system over time. Because the outer regions are held less tightly than the inner ones, they yield first. A small bend in an image means a vast rearrangement in space. A galaxy's shape can twist because dark matter is guiding it. We cannot see it, and still its gravity helps decide how a galaxy moves and settles. If a galaxy sits inside a halo that is not quite aligned with its visible disk, the ordinary stars and gas will respond over long ages, and the disk may slowly twist or warp in answer. So the geometry we can photograph becomes a clue to the shape of something we cannot. A visible form, partly guided by an invisible framework around it. That is a strange and lovely thing to sit with for a while. Invisible mass leaves visible traces in starlight. Dark matter gives off no light of its own, and yet its gravity shapes the motion of stars, the structure of disks, and the outcome of every galactic encounter. Where it is distributed unevenly, the luminous material responds in ways we can measure. Warps, unexpected orbits, streams that curve more than they should. Astronomers are reading effects rather than seeing causes, which lends the whole field the quality of a long, gentle investigation. The mark is there in the image. The thing that made it never appears. Because their structures and motions are unusual, these galaxies act like experiments the universe has already run for us. A warped disk, a polar ring, a counter-rotating center, an unexpectedly diffuse system. Each one reveals how mass must be arranged, if the behavior we observe is to make any sense. That makes them valuable tools for tracing dark matter and hidden gravitational influence. Ordinary galaxies help too, of course, but the odd ones give extra leverage. Their strangeness is not a distraction from understanding. It is very often the route toward it. A galaxy can look baffling in a photograph and become coherent the moment it moves. It may seem lopsided or oddly assembled in ways that resist interpretation. And then astronomers measure how its stars and gas travel, rotation curves, velocity maps, the small shifts in its light, and the mystery sharpens into a story. What looked disordered turns out to be the settling of acquired material, or a disk responding to hidden mass. Motion rescues meaning from shape. Once you let these galaxies move, many of their strangest forms begin to feel almost inevitable. For a long time, we imagined the early universe would show us simple beginnings, small, young galaxies growing patiently toward the grand forms we know. When astronomers finally looked that deep, some of those ancient systems already seemed remarkably unusual. They appeared bright and compact and clumpy, and in a few cases further along than the older models comfortably expected. Instead of a plain opening chapter, the early universe looks busy and inventive. These first galaxies do not feel like rough drafts of later ones. They feel like early experiments, tried boldly and at speed. The farther out astronomers look, the farther back in time they see. In that distant era, many galaxies did not resemble the elegant spirals and smooth ellipticals that feel familiar now. They often appeared patchy and irregular, with bright knots of intense star formation scattered through them like islands. Their shapes seem unfinished, as though gravity had not yet had time to organize everything into cleaner forms. Looking at them is a little like opening an old family album and finding the earliest photographs are the wildest ones. The young universe did not begin composed. Some ancient galaxies made stars sooner than the models predicted. In the standard picture, matter had to gather and cool before collapsing into the first generations of stars, and that was always understood to begin early. Even so, some observations suggest substantial populations of stars had already assembled remarkably quickly. It touches a very large question: how quickly structure can appear after the beginning. If stars formed sooner and in greater numbers than expected, our models of gas and growth may need adjusting. The universe seems to have wasted very little time. The James Webb Space Telescope opened a new window on the early universe, and through it, several galaxies looked more substantial than many had anticipated. Certain distant candidates appeared bright and structured, and in some cases, rich enough in stars to raise immediate questions about how quickly such systems could have come together. First impressions in astronomy are always provisional. Careful follow-up and spectroscopy still matter enormously. But the surprise was real and wonderfully productive. It reopened a good argument about how fast galaxies grew up in the first place. In the young universe, matter was spread unevenly, and gravity wasted no time with the difference. Small clumps drew in more gas and dark matter. Nearby systems met, mingled, and combined. Rather than growing only through quiet accumulation, many early galaxies may have expanded through repeated gathering of their neighbors, which would help explain why so many look irregular and only half arranged. They were not isolated islands developing at leisure. They were part of a crowded age of assembly, in a universe still learning how to organize itself into anything at all. An unusual galaxy is not only something to admire, It is evidence about process. Every time astronomers find a galaxy with an odd shape or motion or history, they gain a clue about the forces that turned a nearly uniform early universe into the richly structured one around us now. Rings, warps, bursts of new stars, faint diffuse systems, and brilliant centers each reveal a different way that matter answers gravity over time. These galaxies are grammar lessons in the language of cosmic construction. The exceptions are often what tell us most clearly how everything else was built. Because light takes time to travel, distance becomes a kind of gentle time machine. Nearby galaxies show us later chapters. More distant ones show us earlier ones, when galaxies were younger and less settled, and often less tidy. So the deep universe grows steadily more unfamiliar the farther we look. Galaxies appear clumpier, meetings seem more common, and the neat categories begin to blur at the edges. It lets astronomers watch galactic history unfold backwards. The elegant systems of today give way to rougher ancestors, as though the universe were slowly shedding its polish. Sometimes, a galaxy looks unusual for a reason that has nothing to do with the galaxy. If something very heavy lies between it and us, a foreground galaxy, or a whole cluster, that mass bends space itself, and the light of the background galaxy is drawn out into arcs and smears and long, soft curves. This is gravitational lensing, and it produces some of the most surprising sights in the sky. The distortion carries information too. Its pattern reveals the mass of whatever lies in between, including the dark matter we cannot see directly. Gravitational lensing can turn one galaxy into arcs, or mirrored pairs, or a ring. When a massive object sits almost exactly along the line of sight to a more distant galaxy, its gravity bends the background light around it. And if the alignment is close to perfect, the result can be extraordinary. A single galaxy appearing as several images at once, or curved into a nearly complete circle of light around the foreground mass. These look like deliberate artwork, and they are simply general relativity working at scale. The sky becomes an instrument. Space itself becomes part of the telescope. There is something quietly companionable about a lensed image, because two things made it together. Massive objects curve space, and light simply follows those curves. So a distant galaxy may reach us bent, doubled, drawn long, or wrapped into part of a ring, not because it is shaped that way, but because of everything it passed on the journey. Appearance, in astronomy, is not always local. The picture holds the galaxy and the long road both, and it took billions of years to arrive. There appear to be galaxies with very little dark matter, and that is genuinely puzzling. Dark matter is usually treated as one of the basic ingredients of a galaxy, which is why reports of systems that seem to lack it drew so much attention. Perhaps they were gently stripped by a passing neighbor, leaving their stars behind, while much of the hidden mass drifted away. Perhaps they formed under conditions we have not seen anywhere else. Perhaps the measurements are telling a more complicated story than we first understood. A handful of exceptions matters a great deal because it asks how universal our models really are. If some galaxies seem short of dark matter, others seem steeped in it. In these systems, the visible stars may be sparse and faint, and yet their motions imply a far stronger gravitational field than the luminous material could ever provide. The dwarf spheroidal galaxies near the Milky Way are the classic examples, holding relatively few stars for the mass that must be keeping them together. There is a lovely inversion here. The stars look almost incidental, while nearly everything that matters is not shining at all. Some galaxies have stopped making many new stars and simply shine on. Their older stars continue to glow, while the process that once renewed them has largely come to rest. The gas consumed, or carried away, or kept too warm to gather. Astronomers describe such galaxies as quenched, which is a gentle and accurate word. The light has not gone out. Only the making of new light has slowed. It gives galaxies a real life story, with seasons of growth and upheaval, and long quiet afterwards. Such a galaxy is still beautiful. The beauty has only changed in character. A galaxy that has finished forming stars is not empty, and it is certainly not dark. What remains is often a grand concentration of older stars, cooler and redder than the hot blue ones that light up busy regions. And together, they give the whole system a warm, reddish glow that feels almost dignified. It is a steadier beauty than the sparkle of youth. Even long after a galaxy stops making new stars, it carries the accumulated light of countless earlier generations. The color itself becomes a way of reading its age, written gently across the whole. A galaxy can lose the material it would need to make new stars and still continue for billions of years. The stars already there keep to their orbits. The overall shape holds. The galaxy still shines, still carries its mass, still shapes everything near it. What changes is only its future. Without enough cold gas, new stars grow rare, and the system feels altered rather than ended. Galaxies are more durable than intuition suggests. This is not an ending so much as the closing of one chapter, with the light of earlier ones still traveling outward. Some of the loveliest galactic forms are not the product of calm. Rings, long tidal streams, nested shells, arcs, warped disks, and bright seasons of star formation usually arise because something arrived, or passed close, or was gathered in. Their beauty is not separate from their upheaval. It comes through it. A graceful ring may mark a crossing. A delicate shell may hold the memory of a companion. This is the part that surprises people new to the subject. In the universe, some of the most elegant structures are aftermaths, and they can look almost designed. 3 quiet ideas run through all of this: meeting, gathering, and time. Meetings reshape galaxies, drawing out tails and forming rings and folding old structures into new ones. Gathering pulls gas inward, feeding the centers and lighting new stars. And then time works over all of it, keeping some marks, softening others, turning eventful chapters into forms that look perfectly composed. The universe is not building from a fixed plan. It is building through process, through pressure, through repeated change. And the odd galaxies simply show that work most clearly. Every unusual galaxy is a record of forces too large to picture properly. Tails stretch farther than whole galaxies. Halos of dark matter guide motion across distances we can barely name. Mergers unfold over spans of time in which all of human history disappears entirely. To study one of these galaxies is to meet gravity in a form well beyond daily experience, no longer a falling apple or a planet in orbit, but the architect of structures 100,000 light years across. Each odd shape is the handwriting of something immense, and we can only read it slowly. The stranger a galaxy looks, the more history it is probably holding. An unusual shape is rarely accidental. A warped disk suggests old pulling or material that arrived from somewhere. A shell hints at a companion long since taken in. A bright center points to matter drifting inward. So, oddness becomes an invitation to ask what sequence of quiet events could possibly have produced it. In that sense, strangeness is simply history made visible. A galaxy with an unusual look is carrying several chapters at once and letting a little of the past show through its shape. To watch these galaxies is to see a universe still trying things. Some combinations of matter and gravity and time make rings. Some make long ribbons of starlight. Some make faint, wide, scattered systems that barely show at all. And some make great smooth remnants, warm and red, resting at the centers of clusters. None of it is finished. Somewhere out there, tonight, in complete silence, two galaxies are leaning toward one another, and they will still be leaning long after everyone who ever wondered about them has gone quietly to sleep.